faithfully conveying value and interpreting great books worldwide.
Hello, this is Sally with Book Talks.
Today, the book we're interpreting for you is The Poetry of Atoms, subtitled Eight Invisible Elements Connecting You and the Universe. Oh, did you know? The iron in your blood is the culprit from a stellar explosion 200 million years ago. The sodium in your tears comes from ancient seas that vanished long ago. The calcium in your teeth was mined by mushrooms from rocks, and the carbon in your breath was once part of a tree trunk, or even part of Einstein's body. These atoms in your body come from all things in the world. In a sense, you're made of lifeless atoms from the universe. This book starts from the atomic level connection between humans and all things, telling the story of the eight most important elements: oxygen, hydrogen, iron, carbon, sodium, nitrogen, calcium, and phosphorus offer a brand new, extraordinary scientific perspective to examine ourselves and the world. The author of this book is American scientist Kurt Stager. He holds a PhD in biology and geology from Duke University and is currently a natural sciences professor at Paul Smith's College in New York. He's also a science writer dedicated to explaining scientific knowledge to the public. Next, I'll interpret this book in 4 parts. Part 1, Hydrogen and Iron, the Birth of Humans and Earth. Part 2, Carbon and Oxygen, Humans and Nature's Breath. Part 3, Sodium, Nitrogen, Calcium, Phosphorus, and the Exchange Between Humans and Earth. Part 4, From the Atomic Perspective, What Does Death Mean? First is Part 1, The Birth of Humans and Earth. How was the solar system born? And how were Earth and life on Earth born? This starts with the first hydrogen and iron atoms in the universe. And 13.8 billion years ago, shortly after the Big Bang, hydrogen was first synthesized in nebulae. The birth of hydrogen is of extraordinary significance because without hydrogen, there could be no water. Imagine if there were no water, the world's oceans, clouds, polar ice caps, and 60% of your body's substance would vanish. Your muscles would disintegrate into useless carbon fibers tangled together. Bones would collapse, and cells would melt without cell membrane protection. And all this would happen in an exceptionally dark world. Because the creation of the sun and stars also relies on hydrogen atoms. When the original hydrogen atoms gathered into clumps and became massive enough, dense enough, hot enough to trigger nuclear fusion reactions, the first generation of stars was ignited. In that incredibly brilliant stellar body, powerful forces continuously synthesized new atoms and released vast amounts of energy during the fusion process. This nuclear fusion process repeated over and over, and as the temperature and density inside the first generation stars continued to change, elements like helium, carbon, oxygen, nitrogen, and others were born successively. And so how was the solar system born? And how did these atoms from the universe come to Earth? Well, this is all thanks to the soon-to-be-born star killer iron. Stars maintain their glowing hot state by relying on energy released from internal nuclear fusion. Before iron was produced, the first-generation stars always generated more energy through nuclear fusion than they released, maintaining a stable state where income exceeded expenditure. But when iron nuclei appeared inside the star, everything changed. Iron atoms are special. Today, in our human blood, they're great helpers for transporting oxygen. But inside stars, iron atoms are dangerous killers because iron nuclei are large. Overly large iron nuclei struggle to produce enough heat during nuclear fusion to support the star. Instead, they absorb stellar energy. Thus, as iron atoms increased, the star's energy became insufficient, causing this Earth-sized body to lose its gravitational resistance, and its core suddenly collapsed. What does core collapse mean? It means immense pressure and high temperatures crush the star's iron core into an incredibly dense ball only a few miles wide. According to NASA's Chandra X-ray Observatory, Such pressure equals what's needed to squeeze all humans into a sugar cube-sized space.
As the star's interior collapsed, complex outer collapses and collisions triggered. Seconds later, when outer plasma hit the dense core, a stunning inside-out explosion occurred, releasing vast light and heat, in which light and heat
And it scattered previously formed atoms throughout the universe. This is what we call a supernova explosion. A supernova's brightness is millions of times greater than the sun's. The sun was born from the massive debris of this supernova explosion, forming a rotating star cluster. When dense star clusters produced enough gravitational pull to attract sufficient matter, they triggered new nuclear fusion, igniting newborn stars. This included our sun. Earth's birth also owes to this explosion. As the newborn sun moved away from its birth nebula, fragments and atoms circled it, coalescing into planetary cores under gravity. Early Earth emerged where two hydrogen atoms bonded with one oxygen to form water, and two oxygen atoms interacted to create oxygen gas. A carbon atom captured two oxygen atoms, forming carbon dioxide. These elements from first-generation stars interacted, creating Earth's primordial atmosphere that sustained life. 4.6 billion years later, humans emerged. Water, just hydrogen and oxygen combined, makes up 60% of your body. The rest consists of elements forged through hydrogen fusion. Thus, every atom in your body exists because hydrogen atoms spread from the Big Bang 10 billion years ago. Even the water we depend on originated from primordial hydrogen atoms. Iron, the star killer, might be the universe's most destructive element. Yet it was iron that opened Pandora's box for Earth's life. Cosmologists debate pre-solar details, but Earth's iron abundance confirms parts of the narrative. At least one core collapse supernova sowed our solar system's seeds with its atomic remnants. Now we understand the solar system's origins and hydrogen's and iron's importance. Atomically, Earth and Sun are our siblings. Their stellar debris shares our elemental composition. Now take a deep breath in, then slowly exhale. Feel it? You're inhaling oxygen and exhaling water vapor and carbon dioxide. But you're not the only breathing species. Nature constantly exchanges breath. This is what we'll cover in part 2, breath between humans and nature. If hydrogen and iron laid life's foundation, oxygen and carbon are the true life sources. They're key to breathing and life activities between humans and nature. First is the oxygen atom, governing breath for both humans and nature. As we all know, oxygen is crucial for our breathing. An adult consumes about 0.9 kilograms of oxygen daily. An oxygen molecule has two atoms. When inhaled, oxygen atoms begin their human journey. About 21% of the air you breathe is oxygen. When you inhale, your chest expands, compressing oxygen into millions of alveoli that enter capillaries. In blood vessels, thousands of red blood cells act like fast-moving vehicles, carrying oxygen through miles of vessels to every body part. So how is oxygen metabolized in your body? This happens in mitochondria, cellular workshops. Cells contain dozens to thousands of them, breaking food into electrons, hydrogen ions, and CO2. Here, inhaled oxygen combines with hydrogen ions to form water molecules, your body's metabolic water.
Over recent days, 1/10 of your venous fluid was produced this way.
Meanwhile, cellular CO2 leaks into blood, enters alveoli, and you exhale it with water vapor, oxygen's breathing journey. So how does nature produce oxygen?
Half your oxygen comes from land plants, part from ocean algae, and the fraction from atmospheric water vapor decomposition. How do plants make oxygen?
Plant cells contain workshops called chloroplasts that convert water to oxygen. Chlorophyll extracts electrons from water molecules and releases oxygen atoms. These free oxygen atoms pair up to form gas molecules, oxygen gas. But plants consume oxygen too. Some new oxygen gets used by them, while the rest escapes into air, eventually visiting your lungs. Imagine the atomic level relationship between you and a nearby plant. If you and your plant spend hours together in a bright room, you can play a game cycling specific oxygen atoms. When you inhale oxygen released by the plant, your cells turn it into metabolic water, which escapes as vapor and drifts to the plant. If that water molecule enters a leaf, new oxygen gets produced. But with humanity's rapid growth, will plants produce enough oxygen? Fortunately, the answer is no. Forest researcher David Nowak notes that just urban trees in the U.S. produce 67 million tons of oxygen annually, enough for two-thirds of Americans. Truly, if we protect forests and oceans, oxygen supply isn't a concern. Beyond oxygen, carbon atoms act as currency in nature's interconnected economy, key to life activities. An average adult carries 13.6 to 18.1 kilograms of carbon atoms. That's about 8 times 10 to the 26 carbon atoms, an astronomical number. Most carbon compounds you eat, like bread or rice, get converted to energy for bodily functions, while 1/10 becomes bodybuilding material. Finally, some carbon atoms exit as CO2 through exhalation, completing their bodily cycle. Recall those mitochondria in cells mentioned earlier. In these workshops, bread gets shredded. Carbon atoms loosen from food molecules, becoming free-floating CO2, released with every breath. But how does cellular CO2 exit your body? This introduces a famous physical phenomenon, Brownian motion. In the microscopic world of atoms, all particles are constantly moving. Even in the calmest pond or hardest iceberg, atoms are always trembling. Not because of cold, but because of heat. This ubiquitous molecular thermal motion is Brownian motion, one of the most unpredictable movements. This physics phenomenon is closely tied to your metabolic cycle because our cells have two transport methods. One is directional movement, like trains delivering goods to distribution centers. When you need controlled directional movement of large substances, your body engages muscles and bones, but it consumes energy. For example, stomach muscle contractions help move and process food, but another transport method is more economical, cost-free, low energy, Brownian motion. Brownian motion is perfect for short-distance transport. Truly, all cells rely on this thermal motion for their metabolism. Carbon dioxide molecules driven by this motion leave cells as metabolic gas. The CO2 we exhale comes from the biosphere, volcanic eruptions, and ocean gas emissions. But in urban areas, about 1/4 of CO2 comes from fossil fuels. From carbon's perspective, fossil fuels are our long-buried relatives. When we talk about fossil fuels like coal, oil, and gas, we're really talking about ancient carbon-based life. For instance, when you hold coal, those carbon atoms in your hand are from long-dead trees, grasses, and moss. That's fundamentally why coal can burn. Atomically, it resembles purified wood, decomposed over geological eras and buried under high heat and pressure. In contrast, oil is liquid, flowing with carbon-rich molecular chains. For oil, the main source is marine plankton. Land plants store energy as sugars or starches, but these dissolve or swell in water. Thus, algae build carbon atoms into hydrophobic oil droplets for energy storage, similar to human body fat. When algae die, oily cells deposit onto the seabed. There, they're repeatedly squeezed and cooked, eventually turning into flammable liquid. The last of the three major fossil fuels is natural gas, which is methane. Newly buried plants and plankton breed bacteria and produce natural gas until rising temperature and pressure kill them too, leaving the gas hidden in coal seams or oil fields. Why are these fossil fuels considered our relatives? Because when burned, they release CO2-rich exhaust, which plants absorb through photosynthesis and turn into carbon-based organic matter that enters the food chain. When we eat those plants, or when animals eat them and we eat the animals, we absorb those carbon atoms. Eventually, some carbon atoms become part of our bodies. Through Earth's carbon cycle, we end up sharing atoms with these fossil fuels. So atomically, a big part of your body is made of air pollutants. Sounds wild, huh? But it's true. In the 1760s, before the Industrial Revolution, our ancestors breathed air with about 280 CO2 molecules per million. Now our air has about 400 CO2 molecules per million. This extra CO2 comes from fossil fuel burning over 2 centuries. Oh, it's tiny compared to oxygen's abundance, but this little bit can melt huge glaciers and mess up ocean chemistry. And similarly, its proportion in your body rises, negatively affecting your breathing and heart systems. Global CO2 concentrations have been climbing since the Industrial Revolution. Scientists predict it'll double pre-industrial levels by century's end, so switching to cleaner energy is urgent. The atmosphere becomes you, and you become the atmosphere. Your breath, every nutrient swap in your cells, is deeply tied to nature. That's the insight from oxygen and carbon. Now, let's look at the soil underfoot and rocks deep down, where four other key elements form your bones, build your muscles, and keep your body in balance. That brings us to part 3: sodium, nitrogen, calcium, phosphorus, and exchange with Earth. First, saltiness originates from one element: sodium, sourced from rocks and soil. Sodium flavors your sweat and blood, helps nerves transmit signals, and aids your perception of the world. So, what happens if your body fluids lack enough sodium? Say you drink over 5 liters of water at once. This dilutes sodium atoms in your fluids, with potentially severe consequences. Severe sodium deficiency in cells can cause acute kidney failure or death. Your cells swell,
Then burst like overinflated balloons. This is water intoxication.
Water intoxication also relates to Brownian motion mentioned earlier. Water molecules easily cross thin cell membranes via atomic vibrations, but larger sodium ions get trapped inside. Water enters continuously while salt can't escape. This imbalance causes cellular swelling. Mild sodium deficiency makes red blood cells swell, blocking narrow capillaries, causing oxygen deprivation and lethargy. Severe deficiency often ruptures cells, leading to convulsions or death. Such tragedies occasionally occur, usually during water drinking events, but sodium does far more in your body. It controls your nerves, enabling thought, sensation, and countless movements.
In your neural network, signal transmission relies on sodium's Brownian motion.
Take deciding to wiggle your toe. Your brain sends signals at approximately 30 meters per second, triggering sodium diffusion cascades. They race down your spinal cord at speeds exceeding 322 kilometers per hour. In an instant, signals traverse your leg to the toe.
After muscles pull your toe, sensory neurons fire sodium waves back to the brain, reporting mission accomplished.
So where does this vital sodium come from? Most sodium in your body comes from salt. Sodium chloride, a compound of chlorine and sodium. Sodium chloride is an edible mineral from Earth's crust. It melts in your mouth, stimulates taste buds, enters your bloodstream, and sometimes spills from your eyes, like tears of joy or sorrow. The sodium in your body originated from solidified magma or weathered lava. When rainwater and groundwater saturate rocks, water extracts sodium ions from stones, carrying them downstream to oceans or closed basins. Chlorine atoms typically escape lava as hydrogen chloride, the same acid in your stomach. In nature, most hydrogen chloride drifts with volcanic ash plumes. Geologists estimate volcanoes release it into the atmosphere annually. Millions of tons dissolve into raindrops and eventually flow into the sea. Thus, in the sea, sodium and chlorine atoms meet, forming salt. Global ocean salt totals approximately 50 quadrillion tons. Extracted, it could bury all land under 150 meters of salt snow. Another element binding us to soil is nitrogen. Though nitrogen makes up only 3% of your body weight, it's key to thousands of life-sustaining proteins. 10 to 15% of your muscle mass is nitrogen atoms. Hemoglobin in your blood has 4 nitrogen atoms, forming a cradle that holds an iron atom. All enzymes, antibodies, genes, neuronal ion pumps, and even nasal cartilage contain nitrogen.
Without dietary nitrogen, using just carbon, hydrogen, oxygen, you'd be nothing but fat and body fluids.
Air is 78% nitrogen gas, but we can't use it directly. We depend on soil-dwelling bacteria. Rhizobia bacteria capture atmospheric nitrogen, converting it to solid compounds plants absorb, entering our food chain. We call this nitrogen fixation, literally fixing nitrogen in place. Besides bacteria, there's another amazing natural nitrogen source: lightning. Lightning bolts may be thinner than your thumb, but hotter than the sun's surface. This extreme heat tears nitrogen molecules apart, allowing oxygen to bond with free nitrogen atoms. Each thunderous strike leaves nitrogen oxides that diffuse through the atmosphere. eventually falling with rain or snow to be absorbed by plants and enter food chains. It's almost certain you carry such lightning remnants within you right now, like most living beings. Scientists found ammonia from natural fixation makes plants grow exceptionally well with astonishing yields. Um, but nature's nitrogen fixing capacity is limited and can't meet agricultural demands. So, around 1909, scientist Haber invented artificial fixation, saving masses from famine. Through Haber's method, using air, coal, and water under high pressure, he synthesized ammonia, turning atmosphere into a nitrogen mine. Agriculture proponents praised it lavishly. This is producing bread from air. Moreover, Haber's ammonia easily converted to nitric acid for explosives production. Pre-artificial fixation, Germany's explosives relied on limited saltpeter mines. Thus, Haber's invention prolonged bloody wars. The cruelest irony. Haber, a German Jew, developed nitrogen pesticide Zyklon B for crops, later used by Nazis in gas chambers to murder millions of Jews. Victims included some of Haber's former colleagues and distant relatives. Beyond muscles, fat, and fluids lies a crucial yet overlooked part, our bones. Composed mainly of calcium and phosphorus, solo calcium ions regulate heartbeat and blood clotting. Phosphorus forms cell membranes and stores, releases food energy. But when calcium and phosphorus combine into hydroxyapatite, they powerfully support your body. Your 206 bones serve as calcium phosphorus reservoirs. About 2/3 of your bones are mineral hydroxyapatite, making up 3% to 5% of your body weight. This calcium and phosphorus come from our food, but trace it back, they originate from underground rocks, mined by soil fungi that deliver them to our tables. Imagine apatite rock in a forest, formed 450 million years ago from coral reef sediments. Buried deep, soil fungi mined its phosphorus and calcium, even killing or digesting insects to send their atoms through roots to nearby plants.
Then a deer eats those phosphorus calcium rich plants, eventually ending up on human dinner tables.
Recall that original apatite, ancient snail fossils still faintly visible on it.
Today, calcium from their shells has journeyed atom by atom to become our bones and teeth. Though phosphorus reserves seem abundant, U.S. Geological Survey reports approximately 1.4 billion tons in the U.S. alone, theoretically enough for 370 billion people, 50 times current population. Yet, scientists warn phosphorus may be Earth's most limiting resource for population growth. Why?
Visionary scientists point to our extravagance as the core issue.
80 to 90% of phosphorus extracted from land never reaches our bodies. Some becomes fertilizer, but at least half isn't absorbed by crops before roots can take it in. Rainwater washes it into groundwater or rivers first. Thus, fertilizer often exceeds plants' actual needs. We even add phosphorus to cattle feed. This phosphorus often becomes unrecycled manure and food waste. Farm-to-table losses mean only a tiny fraction of mined phosphorus reaches us. While these atoms don't vanish, most end up in unrecoverable places, mainly lake and ocean floors. Many scientists warn that phosphorus, like oil, is a finite resource. Its shortage will hugely impact humanity. The only solution is to avoid human waste of phosphorus. After all, humans and all things are deeply interconnected. Atomically, wasting phosphorus is wasting human life. All right, we've learned that, like all things, we're made of lifeless atoms, and we know the 8 elements crucial to our lives. Now it's time to contemplate death from an atomic perspective. Who am I? We usually think of our bodies as solid, well-defined entities. Every morning, you expect to see the same self in the mirror, and people believe you should be responsible for your past actions. But atomically, the you now won't exist after this moment. And your past actions were just done by a temporary collection of particles that no longer belong to you.
Within a year, about 98% of atoms in our bodies are replaced by others.
From air, food, and drinks. As Bill Bryson repeatedly mentions in A Short History of Nearly Everything, any atom in your body now won't be yours in a few years. And human bodies are constantly recycled from fragments discarded by others, or things in the past. In this sense, we're all living dead.
Like the 17th century poet John Donne.
Who wrote, "No man is an island entire of himself. Every man is a piece of the continent, a part of the main." Your atoms connect symbolically and physiologically to Earth, its inhabitants, the solar system, and even the broader galaxy. So there's no need to fear death. According to the law of conservation of energy, not a single bit of you disappears. It just becomes less orderly. As the Bible says, "For dust you are, and to dust you shall return." Most of your body will become gases, carbon dioxide and water vapor. In a crematorium, after hours, atoms you took from the air will depart. The remaining atoms from rocks and soil will be handed to your family as about 2 kilograms of ashes. Your ashes are mainly calcium phosphate from bones, with traces of sodium and potassium. That's all that remains of your body. Most of your atoms will scatter in the air, while the rest depend on how your ashes keeper handles your story. Is this the end? Not necessarily. For these atoms, your death isn't their end, just a new page in their epic saga that began billions of years ago, with the story continuing long after. Where will your vaporized molecules go? The water and CO2 from cremation will travel with winds to Earth's farthest corners. Their atoms will weave into trees, release as oxygen in forests, or become metabolic water again inside your descendants. Some atoms will be torn apart by cosmic and solar radiation. Hydrogen atoms reaching the upper atmosphere might scatter into space via solar wind. Rest assured, death will take your atoms. Thus, countless beings will thrive in the future. For 13.8 billion years before now, you were in a state of death. Only in recent decades have you lived. Statistically, life is far more accidental than death. Nothing lasts forever, yet you've always existed. That concludes our interpretation of The Poetry of Atoms, 8 Invisible Elements Connecting You and the Universe. Reading notes are below the audio. See you next time.